we're back. This is example 10.10, and we just were talking about the requirements for an elastic collision, and that means that that momentum initial must equal momentum final, and also initial kinetic energy must equal the total final kinetic energy as well. Okay, so we have a scenario here with an elephant, and actually, one thing I should also write down is these two equations that we derived. Actually, I didn't derive for you, but that I said could be derived from these two conservation of momentum and energy equations, and that was this: that V initial final. Okay, so this is the final velocity of an object, is equal to mass 1 minus mass 2 over mass 1 plus mass 2. All that times the initial velocity of object 1. Okay? So that's for finding the final velocity of object 1 right there. How about for the final velocity of object 2? And again, this is a scenario where we have object 1, which is moving, and I'll draw this in just a second, and object 2, which is initially not moving. What is their final velocities after they collide? That's what we're trying to find here. So velocity 2 final is going to be equal to, and I'll put this in brackets as well, 2 times mass 1. Change that M there. Could be better. There we go. Mass 1 over mass 1 plus mass 2. That times initial velocity of object 1 as well. Okay? So let's draw a free body diagram. Heck, let's just draw an elephant. Okay? We're going to have an elephant, as we're told, charging out of the brush. Now, actually, before I do, we should point out that there is no mass here. So don't be scared off by that. All we know is the velocity of the elephant. But let's draw a little diagram, and we can, I think we can make this work. So, there's my elephant right there, and he's not very good legs, but whatever. Okay, here's our elephant head, and he's charging out of the brush. Okay, and there's a fly here. I'll make the fly red so it stands out a little bit better. Sorry, our elephant is 1 and certainly does have an initial velocity of 1. Okay, and here's our fly. Our fly is going to be hovering right here, and even though he's flying, he's not moving. Okay, there's no motion associated with this fly, so our fly, even though he's hovering in the air, is essentially at rest. Okay, and we know the initial velocity of object 1. Oh, sorry, our fly is object 2. Okay. It's 2 right there. So the question is, how fast is the elephant and the fly going to be moving after they collide? We might say, well, we have to know their masses. And the answer is yes, kind of. We don't need to know their exact masses in order to understand the principle here. We simply need to know their relative masses. Let's say that our elephant is a lot bigger than the fly, which most elephants are. Okay, so the mass of the elephant, let's say mass of the elephant is 100,000 times the mass of the fly. Okay, we don't need to know their actual masses, but if there's a giant discrepancy here in mass, we're going to see what happens with the two objects' velocities after they collide. So we'll just say the elephant is, the elephant is 100,000 kilograms. I don't think they get that big. And it's also true that if a fly is 1/100,000th of that, most flies don't get to be 1 kilogram in size either. That's pretty darn big, but it doesn't matter. The fact that the size difference is very big, very great. Mass 1 is considerably larger than mass 2. And you know what? I should write these as mass 1 and mass 2, not mass E and mass F for elephant. Mass 1, mass 1, mass 2. This is going to make all the difference, this giant discrepancy in size right here. So if the initial velocity of object 1, the elephant, is 4.5 meters per second, we should be able to find out the final velocity of object 1, the elephant, and the final velocity of object 2, the fly. So let's go ahead and do that. Let's go ahead and do that using these two equations right here. Oops, that wasn't very good. All right, so let's find the final velocity of the elephant. And again, we're just using approximations for mass right here. We don't know if that's the real masses, but we are going to see a pattern emerge with objects that are very, very different in size. So for the final velocity of object 1, that's going to be mass 1 minus mass 2. That's 100,000 kilograms minus 1 kilogram divided by the sum of them, M1 plus M2, 100,000 kilograms plus 1 kilogram. And we're seeing how their great difference in size is going to result in not too much of a change in this fraction right here. And all that is multiplied times the initial velocity of object 1. That's 4.5 meters per second. Okay? What do we get if we calculate that out after our elephant hits our fly? You get something in the neighborhood of 4.999. I think there's 4 nines. Yes. No. 3 nines. Oh, I'm sorry. 4.4999 meters per second. Back up, back up, back up. 4.4999. That's where there's 4 digits, not 4 nines. 4.4999 meters per second. Now, those are too many digits to be significant, but I brought it all the way out to 4 nines to show you that it's actually not 4.5. In some small way, the fly does slow down the elephant. In some very, very small way. Okay, but we're going to see how the elephant affects now the fly. So we're going to solve for the final velocity of object 2, the fly. In fact, you know what? I'll just make him red. I'll make this red so it stands out. And we know it's the fly. So final velocity of object 2. That we're going to use this equation up here for. The final velocity of object 2. Now remember, object 2 was initially at rest. Otherwise, these equations might be a little bit longer, more complicated, but let's plug in what we have for object 2. The final velocity of object 2. So 2 times the mass of 1. So that would be 2 times 100,000. Okay. Divided by mass 1 plus mass 2. That's 100,000 plus 1 kilogram, right? I should really put my units in there. Times, what's this? The initial velocity of object 1, because after all, object 2, the fly, wasn't actually moving. Times 4.5 meters per second. And we're going to see how the fly is affected very differently than the elephant. 2 times 100,000, divided by, what's that, 100,000, and 1 times 4.5. What do we get when we multiply that out? That's going to be the final velocity of the fly. It's going to be 8.9999 meters per second. It's going to be essentially twice the velocity of the elephant. Now, the elephant did slow down ever so slightly due to running into the fly, but the fly resulted in a velocity that was 2 times the velocity of the elephant. The elephant basically ran right through the fly, but the fly is actually going to be shooting off from the elephant at twice the speed that the elephant is going after hitting the fly. So that's just a little interesting scenario where we have a very large object and a very small object colliding, or a very large object colliding with a very small object, and looking at the velocities of the two as they leave that collision. There you go. That's example 1010. I hope that helps kind of understand about elastic collisions. And I'll probably save the next examples and problems for when I get back after the weekend. But I hope this helped, and I'll see you then.